Now say we have a function f of two variables x and y, and it is defined in an open region containing a, b. Then we can define the partial derivative with respect to x at the point a, b by this limit definition, and of course this holds if the limit exists. Okay, so what we are doing, you may note that we are fixing the y variable at b, b here, and making a change only in the x variable. And I'm going to show you a geometric picture of this after we are done with some algebraic calculations. All right. So as an example, let's take up the evaluation of a partial derivative of f with respect to x at the point 1, 1, where our function is defined by 3y over x squared plus y squared plus 1. So what we would do is we are evaluating it at 1, 1. So in the denominator, we have change in x because x is the only variable that we are letting the change, change come in, okay? And y is held constant at 1. And we are letting x vary by h here and let h go to 0. So what happens when we take it like this? Let me just put it below here. That is, all we have to do is this, that substitute 1 plus h for x and 1 for y in this quantity. So we got a 1 here, right? For x, I'm going to substitute in what? 1 plus h, right? And for y, we are going to bring a 1 in here. And for this portion, what we will do is we will substitute 1 for both x and y because we are considering the change starting from the point 1, 1, right? So we got this here. So what does this equal? If you look at it, okay, this equals, we just have a 3 here, right? And then we got a 3 here as well. And here what we have, 1 plus h squared, and this quantity becomes a 2. Okay, all right. Let me enlarge these fonts because I don't know how well visible they are to you all. Yeah, hopefully this is good. Okay, so what we can do is, 3's also cancel. So what we get here is simply a 1. So now what will be a good strategy next? We all have to do this. That is, just take this as the common denominator. Okay. So once we do that, to balance everything, I have to supply that upstairs also. Okay. And now what this will be limit as h goes to 0. And here in the denominator we have h, and in the numerator we have a fraction, right, with this in the denominator, and we got 3 minus this quantity, right, 1 plus h squared plus 2. Okay, so once we look at this, what we have is, let's do this here for space saving. That is, this, I can bring this down here. So h is one factor, right? And this is another factor that we have. I just changed the brackets here. Okay, and then in the numerator I got this, and all we are doing is just reviewing our algebra 1, and doesn't hurt to review it. Okay, so we go here, So we have, let's FOIL it. So if we FOIL it, what do we get? 1 plus 2h plus h square. Okay, so we got that. And then if we simplify the quantity inside the parentheses, what we will have is combining like terms is going to just bring a 3 in here. Okay, now it's time to open these parentheses in the numerator. Okay, so let's do so. All right, so when we open those parentheses, we get 2h, negative sign again, and a negative sign again. These threes will do what? They will cancel each other, right? So what shall we be left with then? See, these guys are out. This simply cancels this here. Okay, and now we can do this. Take h as a common factor because we are taking the limit as h goes to 0. So in there, we are just allowed that we just cannot step on 3, right? So if you take, say, negative h as a common factor, what did you get is, you get 2 plus h as the other factor, right? And then what happens is that we get these h's cancel, okay? And now if you let h go to 0, this numerator will become a 2, and in the denominator we will have a 1 square plus 2. So the value will turn out to be negative 2/3. That is what we have is. So now what we have concluded here is that the partial derivative of f with respect to x at 1, 1 is negative 2/3. Now let's see what's going on here geometrically. Okay, so now to see that how it works, first let us look at a graph of this function. Okay, created by MuPad in MATLAB. So what we had done was that we computed the partial derivative of this function at 1, 1 equals negative 2/3. Okay, so that means if we look at the point with coordinates 1 and 1, okay, so let's look at it. So here we have the point on the surface with coordinates x equals 1 and y equals 1. And now remember, we are doing this, we are holding the y value constant at 1. So this is the y equals 1 plane, and here is the intersection of the surface with y equals 1 plane. All right, and the plane and the surface or the function, they intersect along a curve. So here is the curve of intersection and here is the point. Now if you look at the direction of x increasing, what you find is that the slope of the tangent line is what? Negative 2/3. That's what the partial derivative with respect to x at 1, 1 equals negative 2/3 meant geometrically. Now we can work on it procedure-wise also. Often, or in most of the cases, that is, say we have to obtain df dx, okay? And what we are going to do is that we are going to assume that when we are differentiating with respect to x, we shall treat y as a constant. All right, so this is the expression, and we are going to treat y as a constant here. So when we use the quotient rule, what we do is we shall take the square of the denominator. So first, let's not forget it. Okay, So we squared the denominator, okay? And then what we do is we write the denominator as it is and do the derivative of the numerator, okay, which is d dx of what? Y. I can write y here, and then minus y times the partial derivative of the partial derivative with respect to x of the denominator, okay. So here we go, we are right here, and this is what we got here, okay. All right, and then if we write it again, what shall we get is that see this dy dx, this is going to become 0, right? And y is treated as constant. 1 already is a constant, so d dx of this whole expression would be how much? 2x plus 0, or eventually how much? Simply 2x, right? Okay, so df dx, that becomes here we have a 0, and here we got what? Negative 2xy when we multiply it, okay. Now if we write the value at 1 1, the place there where we just were, then it should be identical, and that is going to be 2 times 1 times 1 will be 1. Let me not write it. And this will be a 1, this will be a 1, and I just made a mistake somewhere. Of course, I realized my mistake, that I forgot this 3 here. You know, we can just put 3 right in front, being a constant. So that would be how much? Negative 6. So negative 6 over 9 would be 2/3, exactly what we had by using the definition from scratch, okay? Now, as I said, that you know, we can compute it mechanically, and we also know the definition, and we will be using the definition and the mechanical procedure interchangeably, and mostly for just later on, for most of the problem solvings, we'll do it mechanically. So let's look at then just this function, the function that I have written here, that what its partial derivative with respect to x will be. So what we are going to do is we are going to use just common differentiation rule, treating y as a constant. So when we do that, what we get here? We have x cubed plus a constant to the power 1/3. So using the power rule, what we get is, we get 1/3, the power steps down, and then we will have what? The quantity, the power on the quantity will go down by 1, and then the derivative of the quantity by the chain rule, right? Okay, so here d dx of the base here, okay. So what we get in this manner, we get 1/3, right? So we have 1, oops, sorry about that, 1/3, okay. This would be negative 2/3, right? So here we have this to the power negative 2/3, and then times what? 3x squared, right? Because we are treating y as a constant, so we get 3x squared, and this is going to be what? Oh, no negative sign, I'm sorry. This is going to be 3's cancel here, So this is going to be simply how much? X square, and then we can bring it downstairs. All right, the power will just change the sign, right? Now notice this. If we do this procedure, then we can see that this procedure is not valid when x equals negative y, because when that happens, what will happen is this, that our denominator will become what? Our denominator will become 0, right? Okay, so it's valid only when x is not equal to negative y. Okay. Now, before we go ahead, let's look at a graph that the MuPad in MATLAB generated for this function. Okay, all right, and what's going on is that whenever x equals negative y, I may not draw the x equals negative y plane, but you know that will be a vertical plane in this direction. So you know, along the line, rather, x equals negative y in the xy plane, we cannot have the partial derivative with respect to x just by using the procedure. So there we will have to use the definition. So let's compute the partial derivative with respect to x, say at 0, 0, by using the definition, because just the procedure doesn't help there, right? So what we are going to do now is that we are going to compute the partial with respect to x, the partial derivative with respect to x at 0, 0 of this function by using this definition that we started with. Okay, so what we have, if we write the values according to definition, both these guys are 0, 0, right? So here we have a 0, b is also a 0, and this is 0 and 0 here. So what do we get? We get the following, that we have this here, that is, we got fh0 minus f0, 0 divided by h. Okay, and then we got this. So what fh0 would be? You can see this here, h cube plus 0 cube. That will simply become how much? That will simply become h cube inside the parentheses, right? And then the exponent would be how much? 1/3, right? And f0, 0 is simply a 0, right? So what happens now is that let's write that in a different line. Okay, so we got this, okay, and we found out that that eventually equals this quantity, which will be here, subtracting by 0 doesn't make any difference. This is simply h. So the partial derivative of f with respect to x at 0, 0 is how much? That's a 1. And if we look at a graph, okay, let's do so. So if we look at the graph, then you can see, oh, well, this is a graph, right? And what we found was that if we compute the partial derivative with respect to x, so as x is increasing, you can see that along the x-axis the slope is how much then? The slope is a 1. And we could not obtain that just by using the quotient rule. Remember, we had to use our very basic definition. Okay.